It may have been overlooked in part due to the emphasis on tracking new mutations on a global scale, right, rather than an individual patient. And this is very cool. I mean, first, listen to this. So in this patient 1, between days 9 and 13, the RNA goes down by 4 orders of magnitude. Okay, from a million to 10 to the 6 to 10 to the 2. Then, however, on day 15 it goes back up again, and then on day 17 it goes back down. So you think, you get infected, it goes up, it peaks, and then it just goes down. It's a little more heterogeneous than that. And then they say this pattern is associated with the emergence of 2 haplotypes on day 11 and 4 minor haplotypes on day 15. So it's just a correlation, right? You see these things going up and down, and that happens to be haplotypes that are associated with that. These variants have 3 independent non-synonymous changes within a single epitope of the N-terminal domain. And they tell us what the amino acid change is. And then on day 13, where there was a low RNA load, they only found the consensus variant. On day 15, there were deletions of a certain number of amino acids or a single amino acid in this epitope. And this accounts for like 26% of the genomes on day 15. Where are these changes in the spike? They are in what they call a super site of vulnerability. Anyway, then they sample it for a long time. So it turns out that this super site of vulnerability is the epitope of a known neutralizing antibody 4A8, and mutations, amino acid changes at that epitope have been found in persistent infections in patients. So it turns out that this the N-terminal domain mutations, amino acid changes, had occurred in other samples that they have as well. So in other words, what we're seeing is we have development of antibodies in the serum, changes in their specificity, and then the emergence of particular haplotypes or particular amino acid changes in the areas that are targeted by this antibody, right? So when the titer goes down, I suppose the antibody is reducing the viral load, and then a variant is in there that's not neutralized, so it comes back up again, right?
Yeah, so basically the virus replicates, goes up to that high peak level, then the immune response starts to bring it down as we kind of classically imagine, but then we have some variant that has the ability to evade that immune response at least a bit, and now the virus is able to start reproducing a little bit more at a higher level and sort of get around that immune response, and so we kind of have this back and forth battle of who's winning.
Right, and then the immune response comes back on the other side, broadens its response more, and tamps the virus back.
Exactly.
And the outcome, we don't know. It depends on the individual patient, right? You may imagine that a particular variant might emerge that patient will dominate and maybe transmit to someone else, right? Mm-hmm. And that's how these variants that are more resistant to antibodies emerge. But we didn't know this before. We had no clue. And they say that we had not seen this before. And they say it may have been overlooked in part due to the emphasis on tracking new mutations on a global scale, right, rather than in individual patients, with a predominance of cross-sectional rather than longitudinal analysis, right? So we just get one sample from a lot of people as opposed to many time samples from fewer. And they also say that, when you take samples from people, you typically use the ones that have good quality sequence, which they say probably early in infection, there's a lot of RNA being produced, and it's going to give you the best sequence. So we're biasing it to before the antibodies have kicked in, right?
Right.
Mm-hmm.
And where the titers are dropping. So I think it's very cool. Now, of course, the sequencing method, too, is totally different, right? Single genomes, which shows you a level of detail you wouldn't see by the other consensus sequencing.